Okay, let me just see for me to share make it in presentation mode. So thank you all for having me. I'm gonna present some of my work that I've been doing for the start of my PhD and with the research group. I'm gonna talk a little bit how we have been using Chapel and how I am using Chapel myself in the way that I'm comparing myself to Chapel. So I'm gonna start with some of the motivations we have within our research group. So the idea is now that with the modern supercomputing landscape, we have even ever more compute nodes. And also the supercomputing now are really heterogeneous. So we have this mix between CPUs and GPUs. And also the CPUs now, they're very, there's a lot of variety within the GPU architecture. So we have mostly Nvidia and AMD. So the idea for us was to explore other types of distributed programming paradigms within the project that could help us reach better scalability within the context of distributed branch and bound, which is a type of tree search algorithm. And the idea to come up with this comparison was that because Chapel uses this PGAS approach to do distributed programming. And this comes up with, in Chapel in particular, this comes with these productivity aspects. And one of the challenges that we have within this type of problems is that we have, when doing branch and bound, we have large and irregular trees. And this will implicate the need for dynamic load balancing and efficient data structures, which also leads to Chapel again, because we can do all these abstraction levels within Chapel and also use the GPUs. But we would like also to provide low-level solutions that we could compare ourselves to Chapel and see how much we gain from using Chapel or how much we would gain from using low-level solutions as well. And here we're going to use as motivating example, the permutation flowshop scheduling problem. I'm going to present a little bit of the background I have for this presentation. So as I mentioned, we are using the branch and bound algorithm. So the branch and bound is a type of tree search algorithm. And the idea for it is that we'll try to solve any type of combinatorial optimization problem using this algorithm, where the search space is a tree and it's based in 4 operators. So the idea is to use these 4 operators to help us reduce the size of the search space. So we have branching, which will help us increase the amount of how we're going to develop the tree. The selection, which will tell us how we're going to run through the tree, how we're going to explore it. The bounding will help us give some estimations that we'll then use to do pruning, which will help us reduce the size of the tree. And we are interested, of course, in doing parallel branch and bound here. So this was one also of the interest within the project to look for this type of language that was using the PGAS programming paradigm and that could offer us a lot of parallelism features. So here we do 2 types of parallelism. So we do parallel tree exploration, which is done on the CPU, and we do parallel evaluation of bounds, which is done on the GPUs for us. So the idea to do the parallel evaluation of bounds on the GPU is because these operations are usually very costly to do these estimations, and we would like to accelerate as much as possible. So if we could estimate thousands and thousands of 3 nodes at the same time, it would be preferential. So again, just to make a quick revision, so why Chapel came up to us. So the idea was that it based itself on the PGAS programming paradigm, and then we wanted to contrast with MPI communication models. Also, Chap has a very interesting feature, which is its native vendor-neutral GPU support. And since 2023, it has support for both GPU architectures, for NVIDIA and then for AMD GPUs. And we also have this feature, which is similar to OpenMP feature, which is the shared memory multiprocessing directives. So for us in the project was the idea that we could have this complete package of parallelism that we could do at the same time for our application in particular. So the objective for us will be for me in particular, would be to base myself in a work that was developed on Chapel, which is particularly this from Helbeck, which is my colleague that developed the Chapel code from 2024 and 2025. And the idea for us is to try to propose an algorithm that is generic in the way it processes 3 nodes, so we could try to treat any type of combinatorial optimization problem. The way we do dynamic load balancing would be, we have the same objective as well. The only difference is that we would use different tools here. So for me, I would use OpenMP while he would use Chapel's features. And then, of course, we would like to use as well GPU acceleration. So for me, of course, I'm going to use low-level approaches, low-level implementations, while he uses on his side the Chapel's native features to do the GPU programming. So the idea in the long term is that we could provide a comparison between the PGAS approach and the MPI plus X approach when doing branch and bound on large scale, like on distributed internode computing. So some of the design we have been using for this particular application is that we first go from a purely sequential application implementation of the branch and bound algorithm, and then we develop the single GPU application. So the idea here is that we're gonna use what we call a pool approach, and then when we do multi-GPU, we're gonna do this multi-pool approach. So the idea is that we're gonna have a pool of nodes, 3 nodes, and then we're gonna send them to the GPU. The GPU is gonna bound these nodes. That is, they're gonna provide some estimations for us that then we could send them back to the GPU, to the CPU, which will then branch and prune them sequentially. The idea here is that because we're doing low level, that we could also try to provide some other features that in principle, we were not able to do in Chapel, but then I'm going to discuss a little bit more about it after. And one of these features that came up for us in one of our last work was about doing GPU thread indexing. So the idea here is that we will provide some information to the GPU, and this information will be used for GPU threads to be able to have a valid computation, so we can use all GPU resources within the code. And then when we go to the multi-GPU design, the idea is that we have this multiple approach, which means that every CPU will have a different pool, and then every CPU will manage a different GPU as well. So the idea here is that for me, we'll be using OpenMP, while in Chapel is going to be used the Chapel directive to do multi-core computing. And then every CPU core we're going to manage a pool, and then we're going to make the communications with one GPU. So the idea here is that all GPUs available within a compute node is going to be used for doing acceleration within the algorithm. Our algorithm is always equipped with intra-node work stealing, meaning that we will be able to deal with the fact that the branch and bound algorithms are usually very, very regular. So this is one of the reasons why also the abstraction in Chapel favors its implementation, because it makes easier to do these transfers. It makes easier to do this balancing between different workloads, especially on the distributed aspect of implementation. And then, of course, we'll have to equip ourselves with determination, because our application in particular is a decentralized application, which means that we don't have a master process, a master thread that's going to manage how the algorithm is it's working, basically. So we have to do this termination condition that has to be looked between all the threads, all the CPU threads. So I'm going to present some of the results we've been having here. So we have tested until now in 2 main platforms. We have been testing the one in Finland, the Lumi supercomputer, and then we've been also using some test beds, some clusters within France, the Grid 5000, so we could have this idea that we could explore both of these GPU architectures. So these are some of the parameters that we have been using, some of the problem characteristics we have been using here. So for the branching bound, we're doing the permutation flowshop scheduling problem, which is basically a scheduling problem, a permutation scheduling problem. The idea to use this particular problem is that the search space is really, really big. We're going to use these benchmarks that are known tie-art benchmarks. And well, the other characteristics are more technical characteristics. So we do use a specific type of bound function that is more costly. This is we say this is a sharper lower bound function. So it's more fit to be used on the GPUs. And then these are some of the implementations we have that we tested. So we did this single GPU implementation, and then we did the test on CUDA and HIP. and also on Chapel on both GPU architectures and also for the multi-GPU implementation. So this has been some of the results we had. So I'm going to run through you then. So here we have the results on the Nvidia architecture on the left, and then we have the results on the AMD architectures on the right. What I call enhanced implementation here is the implementation where we did the GPU thread indexing on the low-level implementation. And then with the standard, it's the low-level implementation that has no GPU thread indexing. And then the gray bars is the Chapel implementation. So here the idea is that we see how much slower is the Chapel and the standard implementation compared to the enhanced implementation. So we can see that we have a very similar proportion between Chapel and the enhanced implementation in both architectures. And when we looked in particular to the multi-GPU here implementation is that we have very interesting results. So we selected mainly four problems to analyze here. So we could see all kinds of behaviors. So we can see that here are the results for the NVIDIA. So the image on the left is basically how these applications are scaling when we are increasing the number of GPUs. So the dotted lines are the Chapel execution times, are the Chapel speedups, and the straight lines are the CUDA speedups. So we can see, and these speedups are the relative speedups. That means we're comparing the multi-GPU results, the CUDA multi-GPU results to the CUDA single GPU results, and then Chapel multi-GPU results to Chapel single GPU results. And the idea to do that here for us is that we wanted to see how good it scales. And we can see that actually Chapel scales better than the CUDA application, than the CUDA implementation, even if when we look at the graphics on the right, it tends to be slower than the CUDA application. And this is mainly due, in our belief, for the good abstraction level that Chapel has, especially when dealing with complicated and complex data structures. So one of the things that is very interesting as well is that when we go to bigger instances, so the 29 is the smallest here, and the 21 is the biggest, is the largest instances on terms of how much nodes we have to explore from the tree. We can see that actually when we do 8 GPUs, Chapel actually managed to be better than when you see Chapel with 2 GPUs. So we can see that it's slower, but not that much slower as when we use less GPUs. So we can see that actually Chapel has this really, really good scalability. And we notice the same behaviors with the AMD GPUs. Maybe the scalability is not as good for the CUDA, but also we have been facing this question that maybe is probably due to the fact that the AMD support is much newer than for the Nvidia GPUs. So this could be also one of the reasons we have. So in conclusion, we can see that Chapel is a really good option and it provides very, very good productivity. It helps us to deal with with these complex data structures in our implementations. But of course, it has some limitations for us, but it's still interesting to be able to use the PGAS, especially on the distributed aspects, which I'm going to comment in a little bit. And I mentioned a little bit about that I was going to mention something about the GPU thread indexing. So more recently, we were in contact with the Chapel support. And then we were able also to implement this GPU thread indexing in Chapel, my friend, of course. And then he was able to remark about 30% in speedup for his own application. So it was really, really good. So we can close the gap between the low-level implementation and the Chapel implementation. And of course, we are more performant when we compare ourselves, the low-level implementation to the Chapel baselines. But on the other hand, Chapel has this feature of having very, very good scalability. So on the multi-GPU side, we see that we have a very efficient implementation of this multiple approach that we did because it presents good results on very different ways of doing things, on very different programming languages. And the good, strong scalability presents itself in both languages. So the multi-GPU aspect, this assures us that this implementation of the multiple approach is really good. And also we have been noticing already some preliminary results for the distributed implementation, and Chapel has presented some very, very good results. So we were able to test on Lumi about 120 128 compute nodes, which is equivalent to around 1,024 GPUs. And we have reached like a speed up of about 100 for Chapel in relative speed up when we compute speed up in regarding to compute nodes. So if compare one compute nodes to 128 compute nodes, we managed to have a speed up of 100, while on the low level implementation, we have around 85. So for future works, we still want to be able to tackle more GPU optimizations and to go as far as we can for the Chapel implementation and also for the low-level implementation. We will have to seek other memory contention strategies because this implementation in particular is very memory consuming. For me in particular, on the low-level side, we would like to explore other ways of managing infra-node shared memory. And then in both cases, that is for Chapel and for the low-level implementation, we would like to go further and provide some more robust results for the distributed implementation and provide distributed dynamic load balancing. And of course, keep providing more feedback on this comparison between the PGAS approach using Chapel and the MIP NPI plus X approach. So this is some of my references. And then if you have any questions, I will try to answer, especially if they're about Chapel, because my friend is the specialist. So, but I have some idea.
I have a quick question.
Excellent.
Sure.
So, you were mentioning that you've got really good performance on a single GPU when you've got these hand-coded CUDA programs, but with multiple GPUs, Chapel's much better, and you attribute that to, Chapel's better handling of scalability. Have you considered looking at doing interoperability with Chapel? So writing your kernels in something more low level, but then using Chapel to do kind of the orchestration?
That's a good question. I think we've been thinking about it because like the way, well, just a little remark. So like on the single GPU, yes, we have these much better results. So, and here on the multi-GPU is actually that the scalability is really good on Chapel, but when we look at really at performance, of course, the low level is more performant than the Chapel one. But this is something we have been discussing about on how to use Chapel and to orchestrate. So my friend has this already this distributed implementation. And then we have been discussing on how to maybe improve how the PGAS space is being really used, like the global address space, and maybe use more this interoperability, as you said, with more low-level options and then we could use these PGAS approaches to maybe implement and accelerate other parts of the implementation side. But this is something we have been thinking. For now, my friend is doing basically pure Chapel implementation. But that's it.
Yeah, this
So
is really cool from a point of, you can use Chapel to write your code much faster and then
yeah,
start replacing pieces with CUDA as you need it to be faster for certain parts. So very cool.
yeah, sure. This is one of this is one of the ideas. Yeah.
Awesome. Other questions? I actually do have a question, and that's if you'd be interested in sharing or like could share any like like the differences in the experience of programming. So like these two different versions. So like either like the sort of size of the programs or like your sort
Yeah,
of
sure.
subjective experience.
Yeah, sure. Well, I would say that for the intranode level, so for the intranode programming, I would say low. So for the single GPU and the multi GPU, like Chapel tends to be shorter, but not that much shorter. But now that we are coming up with these distributed implementations, there's no comparison at all. Like, so what my friend does has, I think, around 60 to 70% of the lines I have. So like if I have a code that has like 1,000 lines, he may have around 600 lines that does similarly. I mean, the way we implement our distributed load balancing is not the same, of course, but we try to make it similar as possible in some way, in some sense. But yeah, and of course, the way you can use the global address space, of course, makes it stuff much easier when you're doing the implementation. So yeah, this is something that also is kind of like making work slower because when we have to do all this MPI stuff at this level, like managing all these compute nodes and this hybrid programming, it's very complicated. So yeah, of course. So this makes it much easier with Chapel.